What does the word cloud mean? It is easy to visualize when we hear it. The image comes to our mind. It is quick and informative, like a brainstorming activity we've been doing since childhood. The activity engages everyone in the class in healthy discussion. The actual definition of cloud computing is provisioning of on-demand services over the internet. Services are available over the internet whatever you require or demand, and you can use it. Let's take a real-life scenario. There was this startup business that is going big. It's expanding. So you require more employees, and those employees need storage spaces. You will provide the hardware resources necessary for them. The data by different users will be stored. It can be retrieved and edited by others, which can lead to data redundancy. Maintenance of those hardware resources is required. The cost increases, and so in order to avoid all of this, cloud computing has been represented as a solution. We all use cloud computing in our everyday lives, Facebook being the most famous social media. Facebook has bought space on cloud. People create user accounts on it and thus use that space on the cloud for connecting with each other. Google Photos is another example. If we delete a photo from our phones, we can always get it back if the phone is synced with Google Photos. Then you have services like Dropbox, YouTube, Amazon, Compology, and many more. There are certain cloud service providers like GCP, AWS, and Azure. And many more companies are trying to launch their cloud services to get it to the business as they know this is the future. So all in all, it is a win-win situation for hosts and customers. Let's take a look at the evolution of cloud hosting, started with dedicated server hosting. One physical device supporting a single project-focused business is what a dedicated server hosting would look like. It runs only one project, it is very expensive to own and run, and requires high maintenance and provides a very high level of security. Then comes virtual private server hosting, where a single business-specific physical machine exists. Sub-machines are created by virtualizing the real machine. It can run a number of projects and it has improved isolation and use of resources. Now we're going to start moving towards the cloud and talk about shared hosting. Hundreds of businesses share a single physical machine. It relies on the fact that most tenants underuse their resources, and it is very versatile. It is highly scalable, safe, economical, and very highly configurable. The most popular and notable hosting solution nowadays is cloud hosting, where several physical systems function as one. The system has been divided up into several cloud services, and it is extremely versatile, scalable, safe, and economical. It is also highly configurable. Cloud hosting provides some really strong benefits, these benefits being flexibility, reliability, and the pay-as-you-go model of payment. In flexibility, traditional hosting providers only provide a small amount of bandwidth. Cloud hosting is scalable to meet seasonal or peak traffic demands. When you come to the pay-as-you-go model, by the month or the hour, users only pay for the resources that they really utilize. The flat fees of conventional hosting are not used within this system. And last comes reliability. Because websites and apps are housed on a network of servers, hardware problems do not result in downtime. Traffic is divided and safeguarded as it crosses various network interfaces. GCP overview. The first thing you need to know about Google's cloud platform is that the global network is actually pretty big. The Google Cloud Platform spans 34 regions across 103 zones. There are 147 different network edge locations at this point, and it covers over 200 countries and territories. To build a network as vast as theirs, GCP employed the major use of 3 pillars upon which they made the foundations of whatever they built. The first one is trust and security. It's not ideal to build first and then secure it later. Many problems and vulnerabilities appear using this method. Instead, GCP employs a secure by design infrastructure, meaning that security is built into the very foundations of whatever growth has to come. The second pillar is that GCP employs the use of open source, or when you talk about it in terms of cloud computing, the open cloud model, meaning you can use services, functions, and features that are publicly and readily available for use free of cost on the internet. Last comes analytics and artificial intelligence.
Instead of you having to figure out what the best approach for your business applications and business needs is, GCP does that for you using artificial intelligence and machine learning to figure those solutions out. When we talk about the cloud, it's not actually a physical cloud up in the sky. There are actual physical servers in the form of data centers spanning the regions and zones that cater to the requests. Servers in the same zone are interconnected such that they have an extremely low latency connection. Furthermore, this model allows for disaster recovery as well as high resource availability. These data centers are constantly being upgraded to provide an even higher availability still. Let's talk about the elephant in the room, networking. You can't have a cloud network without networking. On the highest level, networking can be described as follows. Just think of it like this. You bought 1,000 colored pens and the truck just dumped them in your drive. You need a place to put all those pens in, right? So you get a box to put those pens into. That box is the VPC. The VPC is simply a place for you to store your resources, or, in our case, the box to store all our pens. Now the box is completely mixed with black, blue, and red pens, and you want to group them by color. So you cut some sheets of cardboard and you make dividers inside the box and divide the pens by their colors. That grouping of resources is what subnets do. So the subnets, in our example, are the dividers inside the box to separate the pens. Lastly, you need to be able to access the pens so that you can actually use them and take them when you need them. So you cut the box from the top so that you can actually take the pens when you need them. That cutting of the top of the box so that you can access your resources is basically what the router does. It connects your resources to a network so that you can access those resources. Now that you know where your resources go, how to group them up, and how to access them, let's take a closer look at that last part, accessing them. You may not want everybody to access your resources. In fact, you might only want a very select few people to have access to some very select resources. For that, you use firewall rules and IAM. IAM stands for Identity Access Management. What that is a story for a later time down this course. For now, all you need to understand is that you can control the traffic that is both coming into and leaving your network and subnets. With firewall rules, you can set very specific conditions on the type and flow of traffic to your VPC. With IAM, you can set granular policies that will allow you to practice the principle of least privilege. The way you can understand what this means is think of the following scenario. You live in a gated community, and you've hired someone to wash your car. That someone is allowed to come only to your home and only to wash your car. They may not visit any other home or wash any other car. That's the level of access you can have with IAM and firewall rules. When it comes to security, GCP secures you on 6 layers, employing the best security practices in doing so. Let's go through them together. The first one is the device layer. The device and its operations are secured. Then comes internet security. Communications done over the internet are encrypted. Then comes identity. All users have their identities authenticated and validated against the services that they are permitted to be accessing and using. Sensitive data is also protecting using keys. Then comes security of storage. The moment you upload any data to the Google Cloud, it is encrypted at rest automatically, protecting your data against unauthorized access. We're going to talk more about encryption at rest later in this course. Then we have deployment of services. All services deployed use cryptographic authentication and are authorized at the application layer. Lastly, we have hardware security. The hardware infrastructure is Google controlled, secured, and hardened. These are Google's own words to describe the security of their hardware. You may have come across the term API here and there. API stands for Application Programming Interface. It's a fancy way of saying that a service talks to an application and they both send and receive requests and responses from each other. It's important to talk about APIs because when creating applications, you're going to need to employ the use of the APIs to make your application communicate with the Google Cloud services. The way you can use the APIs in your application is by getting the SDK library in the language that you're working in. So say I'm making an application in Python. I'm going to get the SDK library for Python in order to make my application. APIs give your applications access to every service within the Google Cloud Platform, granted that you've set it up correctly. When it comes to working with APIs, GCP makes it extremely simple. You have an entire APIs and Services tab where you can go and monitor what your enabled APIs are doing and ensure that they're behaving as they should be. You can also pick and choose which APIs you want to work with by selecting the required APIs from the API library. To work with APIs isn't as simple as linking an API and it just starts working off the bat. APIs are secured via credentials. You can generate credentials to use with your APIs from this management console. Let's get an overview of databases in the Google Cloud Platform. But first, it's important to understand the two types of databases you have available to you and why you have these two different types of databases. The first one is relational databases. These databases are structured in the forms of tables, columns, and rows, and each table will have a primary key which will serve as the identifying attribute of each item or row in that database. Non-relational databases do not operate on this premise. The data is not stored in a tabular form here. It is instead stored in different ways like graphs or documents. We call these types of databases NoSQL databases, and in order to use them effectively, the applications using them should be able to process and communicate data quickly and have near real-time result delivery. When it comes to relational databases in GCP, you have Cloud SQL and Cloud Spanner. Let's look at the Cloud SQL first. Cloud SQL is a highly available database that provides MySQL, Postgres, and SQL Server engines. The processes of backing up, replication, capacity increasing, and encryption are basically automated. This ensures that you have an availability of greater than 99.95%. Now let's take a look at Cloud Spanner. This is an enterprise-grade, globally distributed, and highly consistent database service that was built bespoke for the cloud. Cloud Spanner provides a dedicated network with low latency, high reliability, and security for its users globally. Now let's take a look at our non-relational or NoSQL databases in GCP. First up, we have Cloud Bigtable. This is a NoSQL white column store for large-scale, low-latency workloads. It was designed to store large amounts of data for each row or item. Cloud Bigtable is often used in applications of machine learning and artificial intelligence for having a high throughput as well as a low latency at scale. Next comes Firestore. This is also a NoSQL database, but this is used towards the development of rich mobile, web, and IoT applications. This is because of how easy Firestore makes syncing the stores as well as querying data for mobile and web applications. Then comes Firebase. This is used to let you store and synchronize data between your users in real time for applications, ads, mobile sign-ins, and in-app chats. Firebase is a powerful tool to use with microservices and web applications. Last comes Memory Store, which is a fully managed Redis and Memcache database. It provides millisecond access to the data. This is typically used in high-performance, scalable web applications.
Let's go through the benefits that cloud computing provides. Rapid scalability is a significant feature and advantage of cloud computing. Due to this cloud feature, workloads that call for a large number of servers but are only needed temporarily can be performed cost-effectively. Such workloads are common among clients and may be managed extremely economically because of cloud computing's quick scaling. There is no problem in going up or down as per your requirements. The cloud's capabilities can be greatly expanded and adjusted depending on their intended application. It evaluates the storage utilization and offers the customers the option to very inexpensively purchase more cloud storage if necessary. With the use of a gadget and an internet connection, the user can view cloud data from any location and post data to the cloud. These capabilities can be accessible through the internet and are distributed throughout the network. The storage devices where the data is kept are secure against hacking and unauthorized use. Fast and dependable storage service is provided. The user only has to pay for the services or space that they really use in cloud computing. There are no additional fees or hidden costs. The service is reasonably priced and frequently some space is provided without charge. Data backup and recovery is among the most advantageous aspects of cloud computing. It takes a snapshot of the data so that even if one of the servers is damaged, the data won't be lost. The servers are simple to maintain and there is very little and occasionally no downtime. Every time, cloud computing improves itself gradually to produce an update. In addition to having issues that were repaired, the upgrades are speedier and more device compatible than prior versions. There are three types of cloud service models that you will encounter when dealing with cloud computing. The first one is software as a service, where the entire infrastructure, operating system, and software is provided by a third party. Then comes platform as a service, where the entire infrastructure and operating system is provided by a third party. Then comes infrastructure as a system, where part of or all of an infrastructure platform is provided by a third party. There are three types of cloud deployment models. The first one is public cloud. This is a cloud service provided by some service providers such as GCP or AWS. You can pay as you go when using this type of cloud. Public clouds are easily scalable and elastic. The private cloud. This is the cloud you technically create yourself. That is to say that this is the on-premises cloud. You have complete control over customizability here and it's the most secure of all options. However, it is really expensive and not easily scalable nor elastic. The maintenance falls upon you and there may be latency issues down the line. Last comes hybrid cloud. This is a combination of both public and private cloud. This is often found when companies are shifting from private to public cloud. Sometimes it's used as a backup option in case of emergency. The shared responsibility model. The GCP shared responsibility model determines which cloud architecture components GCP is responsible for as the cloud security provider and what falls upon the customer to secure themselves. Broadly speaking, Google is responsible for the cloud. For example, the infrastructure and the customer is responsible for anything in the cloud itself, which is to say anything they can configure themselves. Here's Google's breakdown of the shared responsibility model. GCP models holds the customer responsible for securing a substantial scope of cloud infrastructure components, including cloud configurations and data stored in the cloud. So this is your content, the access policies, the usage and deployment, web application security, identity, operations, access and authentication, network security, and guest OS data and content. In short, if you can configure or store it yourself, then you are responsible for securing it. Per the model, as a company takes more ownership of its cloud computing, more components become the company's responsibility. In the infrastructure as a service model, the customer is responsible for anything on top of the infrastructure and network level. In a platform as a service model, Google is responsible for everything in infrastructure as a service and the data, network security, application security, and identities. And finally, in the software as a service model, the customer is responsible for only application usage, access policies, and the content. With this information, you now know how the shared responsibility model is applied within GCP for your own usage. Let's take a look at compute as a comparison example of the shared responsibility model. Starting with infrastructure as a service. So first we have our physical machine and you're basically responsible for everything else and you just want the cloud service provider to take care of the hardware for you. You have control over the host operating system and basically what's going to be installed at the lowest level. And at this level you can control the hypervisor, and if you want to install some different kind of virtualization or no virtualization, that is completely up to you. So for you, You are more responsible for this layer. Then you have virtual machines. This would be compute engine. You are responsible for the guest operating system configurations. You can also install a container runtime, while Google is responsible for the hypervisor and the physical machine. Lastly, let's look at containers. We have different options, but let's talk about containers. You are basically responsible for configuration, deployment, and storage of the containers, and Google will take care of the operating system, hypervisor, and container runtime, and that means you have less and less responsibility. Now let's talk about platform as a service. It is a managed platform, so we have an application engine. Here you have to upload your code. You have some environment configurations. You have to choose the type of deployment strategies that you want. You have to configure any associate service, but Google will be responsible for the servers, operating system, networking, storage, and security. Lastly, we have software as a service. A good example of this is the Google Docs. Here you are responsible for the content on the documents, the management of the files, and the configuration of sharing access controls, and Google is responsible for the servers, operating system, networking, storage, and security. Cloud TCO is a method used to tally the various costs to host, run, integrate, secure, and manage workloads in the cloud over their lifetime. These include fees associated with the resources consumed, such as compute, data transfer, and storage. It also includes integrations with related cloud services ranging from security and management tools to machine learning and AI. Even calculating personnel costs for cloud engineers can be part of cloud TCO equations. Reduction in Capex and increase in Opex yields more flexibility and the capacity to scale usage as required. Let's compare Capex with Opex. Capex stands for capital expenditure, where you pay upfront, it's a fixed sunk cost, whereas Opex stands for operational expenditure, and services and resources are billed on a pay-as-you-go model. It can be difficult to balance capacity against demand in Capex, but costs can be continuously monitored and adjusted as needed in Opex and must be done accordingly. Your budgets must typically be addressed annually at the executive level in Capex. Some key architectural concepts in the cloud are availability, scalability, elasticity, fault tolerance, and disaster recovery. Availability is the ability of your service to remain available by ensuring that there is no single point of failure. A load balancer allows you to evenly distribute traffic to multiple servers in one or more data centers. If a data center or server becomes unavailable or unhealthy, the load balancer will route the traffic to only available data centers with servers. Running your workload across multiple zones ensures that if one or two zones become unavailable, your service or applications remain available. Your ability to increase your capacity based on the increasing demand of traffic, memory, and computing power is your ability to scale, or scalability. Scaling up means upgrading to bigger servers, and scaling out means adding more servers of the same size. Elasticity is your ability to automatically increase or decrease your capacity based on the current demand of traffic, memory, and computing power. Horizontal scaling out means to add more servers of the same size, and scaling in means removing servers of the same size. Vertical scaling is generally hard for traditional architecture, so you'll usually only see horizontal scaling described with elasticity. Managed instance groups, or MIGs, automatically increase or decrease in response to demand or a defined schedule. Failovers is when you have a plan to shift traffic to a redundant system in case the primary system fails. You can use Cloud DNS, which is a DNS service that can detect a failing primary system and fail over to a standby secondary system. A common example is having a copy or secondary of your database where all ongoing changes are synced. The secondary system is not in use until a failover occurs and it becomes the primary database. Disaster recovery is your ability to recover from a disaster and to prevent the loss of data solutions that recover from a disaster. Do you have a backup? How fast can you restore that backup? Does your backup still work? And how do you ensure current live data is not corrupt? These are all questions that are tackled in disaster recovery.